Hey guys, so in this video we're going to be talking about complex numbers. And you may have heard of those in a high school algebra course. May have even thought they were kind of stupid, because they're going to deal with what we call imaginary numbers. And, a lot of people find it a little bit crazy that we have imaginary numbers, numbers that are not real. So the first thing is, hopefully, this course in quantum mechanics will give you an appreciation for imaginary numbers, because there are some branches of physics and other sciences as well that um, are impossible to do, or at least extremely hard to do without imaginary numbers. And you'll actually see that our using of imaginary numbers will give us real answers, and we're going to use imaginary numbers all the time in quantum mechanics. So I wanted to have this review video on complex numbers. So to start, um, well, let's start with imaginary numbers. Imaginary numbers, the imaginary number I is defined as the principal square root of -1. Now, there's actually two things that squared, right, will give you -1. And actually, a lot of mathematicians will prefer the definition that I squared equals -1 to the square root expression. So the square root is double valued. But the principal square root, right, we have I, right? We have I is the principal square root of -1, but you'll notice negative I squared, negative I, right, in parentheses squared, is also going to give you, right, well, let's see, this is -1 times I, right, squared, which is -1 squared times I squared, which is, well, -1 squared is 1, I squared is -1, right? So the square root of -1, right, or if we asked ourselves what number squared gives us -1, it could be either I or -I. Okay, so this is just a definition, right? We don't have any real numbers, any numbers in our regular number system that squared will give you anything negative. And so this definition lets us take the square root of any negative number, right? For example, the square root of -9, right, is, well, this is the square root of -1 times 9. So we'll have is the square root of -1 times the square root of 9. So this is going to give us 3i. Now be careful with this method. Just a quick thing, people get stuck on this a lot. A lot of people will look at the square root of 1 and they'll look at it like this. This is the square root of -1. We'll write this as the square root of -1 times the square root, or the square root of -1 times -1, right? Which works. They'll expand this out, square root of -1 times the square root of -1, and they take this to be I times I, which will give us -1. This answer is clearly not correct, and there is an element of truth to it, which is, right, -1. -1 squared is going to give us 1. Now that is not the principal square root, and just because of how mathematicians define, right, the square root, it's fairly arbitrary. I mean, the square root of 1 really could be 1 or -1, but we define this symbol to only be talking about the positive square root, right? And so the way mathematicians define the square root, this trick won't work if they're both negative, but if only one is negative, it will work. All right, so we have this down. Hopefully this is familiar to you. We're going to be using complex numbers a lot. So next thing, one more thing just about purely imaginary numbers, and then we'll get to complex numbers. I want to talk about the powers of I, right? And there's a really cool pattern to this. So let's start with I to the 0 power. Well, anything to the 0 power is 1, right? I is, again, just a number. It's a little bit special because we call it imaginary, and it's not on the regular number line. You'll see what special number line it's on. But just like any other number, I to the 0th power is 1, right? And I to the 1st power, right, is I to the 0th power times I, or which would also just be, we also know that, like any number, I to the 1st power, something to the 1st power is itself, so this is just going to be I, right? I squared, well, this is by definition -1. What about I cubed? Well, I cubed is going to be I squared times I, right? That's how we increase by a power, just multiply by I. So negative 1 times I, well, that seems like it's going to give us negative I. And what about I to the fourth? Well, I to the fourth, right? Well, this is I cubed times I, right? And so that's I times negative I, which is going to give us, right? We can just move the order of multiplication around. Negative I times I, which is negative negative 1. So this is positive 1. Now, if we look at this a little bit farther, well, let's see. What's I to the fifth? Well, that's going to be I to the fourth, which is 1, times I, which is I. I to the sixth power is going to be, well, I to the fifth times I times I, we know, by definition, is negative 1. Looks like then we'll have I to the seventh, right? I to the seventh is then negative I. And I to the eighth will then, just by the same thing we did here, be 1. Then I to the ninth will be I to the 10th will be negative 1, etc., etc. So this is a cycle alternating between 1, I, negative 1, negative I, 1, I, negative 1, negative I. And using the same logic, working backwards, you can just use the pattern, or you could use the same kind of logic as, you know, what times I will give me 1. We can look at what I to the negative first is, right? And so this is saying, right, I to the negative first times I is going to give me 1. Well, what times I gives you 1? Negative I times I gives you 1. And this presents something weird, something you're probably not used to seeing, which is, right, I to the negative first. Well, we know something to the negative first, that's just, right, it's reciprocal. So this is 1 divided by I. That's just something to keep in the back of your head, that 1 over I is negative I. It's just an interesting thing that complex numbers, or imaginary numbers, do. All right, so hopefully we've got all this down, and now we're going to move on to not imaginary numbers, but complex numbers. And all a complex number is, we generally represent it by the letter Z. Not sure why, but that's just the standard way of writing a complex number. You can represent it as anything, just most textbooks you find will represent it as Z. And the standard notation for a complex number is A plus B I. Where A and B are real. Right? So A and B are just real ordinary numbers. Then we multiply B by I. So we have A is our real part, B is our imaginary part, and A and B are both real, but B is the imaginary part, that's what's multiplied by I. So for example, if I had Z equals 3 plus 2I, right? The real part would be 3, the imaginary part would be 2. Or if I had 3 minus 2I, right? Either part can be negative as well. They just can't, right? They're just real. A and B are defined to be real. And we have this notation, right, where the real part, right? I'm just gonna erase this here. There we go. The real part, written like this, of that Z up there is A. The real part, or sorry, not the real part, the imaginary part of a complex number Z, right, that is A plus BI, is B. So in that example, when I had 3 plus 2I, the real part of 3 plus 2I is 3. The imaginary part of 3 plus 2I is 2. Right? And you could write it, right, something like IM of 3 plus 2I equals 2. Right? So this is really basic. Hopefully we've got this down. I'm going to erase this here. Right? So now we know we can put any number on a number line, any real number on a number line. If you've looked at a number line recently, you'll probably remember that you don't see any imaginary numbers there. Well, we actually have a special number line for imaginary numbers, and conventionally, it goes up and down. So here you have, right, this is the real number line. Here we've got, this is 0 right there. Now, we also have the imaginary number line going up and down. So here, we've got, right about here, we could have 1. Right about here, and that I'm very bad at drawing. You'll see that in this course. We've got I. About here, we've got negative I. And here, we've got negative 1. So, given this, right, we can also plot out any complex number. Because now we don't just have a number line, we've got a complex plane. This is called the complex plane, and it has axes. We have the real axis, which is the x-axis, and the imaginary axis, which is the y-axis. And I really should have labeled it up here, but you'll understand what I'm saying. So for example, if I say I've got 2 right here, and I don't know, this is halfway between, right? This is going to be like I over 2 over here. Well, what is this point? This point is 2 plus 1/2 I, or I over 2, right? The real part is 2, the imaginary part is 1/2, and I should label that in a different color. So this is 2 plus 1/2 I. Or if I had some point, I don't know, over here, this looks like it would be about 1 minus 2I, right? The imaginary part is negative 2. We have that right here, right? So, if you think back to elementary school math, when you add 2, right, you're starting, right now we're starting at 0, we go to the right 2. Well, when we add I, we're going up 1, right? So here, if we look at like 1 minus 2I, we go to the right 1, we're adding 1, then subtracting 2I, so going down 2, and that's where we get. And you can show that with any point on the line. It's just like regular numbers. It's just we're introducing another axis, and then a number that's squared gives you negative 1. You can add complex numbers, subtract complex numbers the same exact way. You combine like terms. So if I wanted to add these two numbers up, right, that would just give me 3 plus 2.5i, which is 3 plus 5/2 I, right? Or we can subtract them the same exact way. We can multiply them out. You just have to distribute out, just like with like a quadratic, right? So these numbers are not that complicated. So the next thing I want to talk about, right before we just get into a few identities to finish off the video, is if I have z is equal to a plus bi, what is the absolute value of z? Right? Well, sometimes you might want to think of the absolute value as like the positive version of a number, right? Which works, right? The absolute value of -5 is 5. The absolute value of just 7 is 7, right? However, with complex numbers, that doesn't exactly work. What's the positive version of 1 minus 2i? Yeah, we really don't, we don't have a good way of defining the positive version. However, you will hopefully remember that, right, even if you think of the absolute value like the positive version, that's not how it's defined, right? The absolute value, you remember from way back in math, is defined as the distance of a number from 0, right? And a distance is always positive. So, and that's on the real number line, right? We're at -5, right, which would be about here. We're 5 away from 0. If we're at 2, we're 2 away from 0. Well, what if we're at I? If we're at I, we're just 1 away from 0, right? It's a length, so it's always going to be positive. It's the length on this coordinate grid. Well, what if I'm at 1 minus 2i, right? How far am I from 0? Well, the absolute value of z, the absolute value of 1 minus 2i, is going to be the length of this line. Well, what is the length? Well, we know from Pythagorean theorem, right? Hopefully you remember Pythagorean theorem, a squared plus b squared equals c squared. And here, right, what's the length of this line? Well, the length of this line is, right, so this is a right triangle with side lengths of 1 and 2, right? This is going to be the square root of 1 squared plus 2 squared. So this would be the square root of 5, right? And so more generally, and I'm going to erase this stuff over here, just more compact. I'm going to erase all of this. You can just see, right, from, if I just draw a simple axis, this is A, this is B, and this is actually BI. this is going to be a plus bi, right? Which is equal to, right, we're saying z. Well, if I want the absolute value of z, sometimes called the norm or the magnitude of z, that's all I want is this length. By basic geometry, I know that this is a squared plus b squared, right? And then square root. And we know that a and b are real, so their squares are going to be positive, and then the square root is positive. So this is, right, the absolute value is always is a length. It's always going to be positive. Hopefully this makes sense. And I'm going to erase this. I'm going to keep this, the z equals a plus bi, and a and b are real at the top, because it's like the base of everything we're doing. All right. So now I want to define what is called the complex conjugate. Complex conjugate. All right. And the complex conjugate of a complex number z is written as z star. And what are we going to do? Complex conjugate is defined is just we're switching the sign on the imaginary part. So a minus bi. All right, this is our definition of the complex conjugate. All right, so now you know, this might seem like a very random thing to define, but we're actually going to see it's got a lot of different uses. The first thing to note is that what is the magnitude of z star? Well, the magnitude of z star is, right, it's a squared plus then negative b squared, right? Negative b quantity squared, because that's the imaginary part, but negative b quantity squared, that's just b squared. So this is root a squared plus b squared. And this is magnitude, the absolute value of z. So a complex number and its complex conjugate have the same absolute value. That's one important thing. Next, I'm going to erase this, hopefully you have it down. I'd like to look at z star times z, and which is also z times z star. It works either way, right? Multiplication is commutative, even with complex numbers. Well, this is a minus bi times a plus bi, which is a squared, right? If we just distribute this out, a squared minus a bi, right? So we're doing a squared, a times a, negative bi times a, and then a times bi. I know usually it's done in the other way. I distributed it in a little bit of a weird order, but hopefully you can still follow this, right? A times bi, and then negative bi times positive bi, right? Negative bi times bi is, well, that's b squared times negative I times I. Negative I times I we showed is, right, so this is times 1, right? Times 1. I'm using x right now, but eventually we're going to not use x because we'll have, you know, x is a variable, right? So this is plus b squared, right? But we notice negative abi and positive abi cancel out, and this is a squared plus b squared, which happens to be the absolute value of z squared, which is also the absolute value of z star squared. So a complex number times its complex conjugate is not only we've now shown that it is a positive number, right? This is positive. It's not only a positive number, but it is in fact the norm squared, the magnitude squared, or the absolute value squared. Again, those words are all interchangeable, of the complex number, which is also the same as the absolute value squared of its complex conjugate. So I'm going to erase my work here. Hopefully you have this down. I'm going to just concisely state what I have here. Z times z star times z is, z times z star times z is the absolute value of z squared, which is equal to the absolute value of z star squared. Now, before I prove the rest of our identities, we've got We have, it looks like 5 more. Um, I just want to state one thing. All numbers are complex numbers. I forgot to say that before. All numbers are complex numbers. And by that, I mean a purely real number is just a complex number with b equal to 0. The imaginary part is 0. A purely imaginary number, right, is also a complex number with a equals to 0. The real part is 0, right? So, and 0 too. 0 is a complex number. It has a real part of 0 and an imaginary part of 0. I, right? Again, I is a complex number. A equals 0, b equals 1. That's just an important thing. Just we're not really going to be using that. That's just semantics. But if you continue on with math, that's an important semantic to know. Right. So I'm going to erase this, and I'm going to erase this up here. I'll rewrite it. Z star. Not switching well. Z star equals A minus BI. All right, so next identity. Z star star. Well, this is A minus BI, right? That's Z star star, which is equal to, now, right, B is just like negative B, right? We're just going to flip the sign of the imaginary part when we take the complex conjugate. So this is A plus BI, which is equal to Z. So apparently, these stars, right, the complex conjugates cancel themselves out. So again, to write that really concisely, right, Z star star, the complex conjugate of Z star is equal to Z. That's an important identity to know. Okay? All right. Now, let's look at, I've got two complex numbers, Z1 and Z2, right? If we just think about it, Z1 is A1 plus B1I. Z2 is A2 plus B2I. Right? So now, let's look at what Z1 plus Z2 complex conjugate is. So, what I think I'm going to do, actually what I'm definitely going to do, is I'm going to state these next 4 identities, and the proofs are extremely easy, right? All you have to do is just substitute these, or if we're only talking about one complex number, just substitute this in, and they are extremely, extremely easy to prove. So I'm just going to state them, and you can either just write them down and take me for it, or prove them yourselves. Again, it's not that hard. You just have to plug in, if I have Z1, you just have to plug in this, Z2, plug in this, and then you just plug in the other side, and you'll find out that they're equal. So first thing is this complex conjugate will distribute in a sum. Right, and this will also work with subtraction, right? It's the same thing, right? Z1, so Z1 plus Z2, all of that complex conjugated is Z1 complex conjugate plus Z2 complex conjugate. My stars are a little bit messed up, but you know what I'm saying. Okay, next one. Also with multiplication, Z1 times Z2 star, right? This is going to distribute out in the multiplication too. Z1 star, Z2 star. All right, let's write this next one up here. We have, this is just now with one complex number, Z plus Z star is equal to 2A, or we also write that as 2 times the real part of Z. And finally, remember this is why I write the dash in there, so we don't confuse 2's and z's. Right? Finally, Z minus Z star is 2BI, right, which is 2I times the imaginary part of Z. And again, you can just prove these purely by plugging this in, plugging these in for everything. Just one comment on this. If I add a number and its complex conjugate, we know that the answer is going to be real, and that's going to be important. That adding something in its complex conjugate will give you something real. Subtracting something in its complex conjugate will give you something imaginary. So that's just an important thing to note about these two identities. All right, so that is everything with really that we need to know about complex numbers. Except in our next video, we'll be talking about what are called complex exponentials. So I'll see you then.